Let's work a few examples. We are given here the half-life of beta decay of carbon-14 is 6,000 years, approximately. You test a fossil and find that only 25% of its original carbon-14 is undecayed. How old is the fossil? So 25%, what's 25%? That means we went 2 half-lives. The first half-life, we went from 100% to 50%. And the second half-life went to 25% from 50%. So 2 half-lives, that's 2 6,000 years. So that's 12,000 years. That's our answer. Okay, now in this question here, we are told that 1 in 8.3 10 to the 11 carbon atoms is carbon-14. So not all of the carbon atoms are carbon-14. Only 1 in this huge number of carbon atoms is carbon-14. And carbon-14 decays with an electron emission, beta minus decay, with a half-life of 5,730 years, 5,730 years. That's what we approximated to 6,000 years here. The question is, determine the number of decays per gram of carbon. Number of decays per gram of carbon. That's present carbon right now. So in 1 gram. Okay, you know that the atomic mass of carbon from a periodic table you can find it is 12 grams. So 1 mole of carbon is going to have a mass of 12 grams. So to find the number of carbon-14 in 1 gram, what we need to do is we divide the number of mole by 12 grams. So it's 1/12 of a mole that we are looking for. How many carbon-14 atoms are in 1/12 of a mole. And then we multiply that by Avogadro's number. So we know how many atoms we actually have there. So 6.02 10 to the 23. And then we divide that by the percentage of carbon atoms that are carbon-14. So this is 8.3 10 to the 11. Okay, so this gives us 6 times 10 to the 10 atoms of carbon-14 per gram. Now, to find the activity R, remember, is minus lambda n. We just found n. Lambda, remember, it is log of 2 over the half-life. What you need to be careful about, the half-life, you have to express it in seconds. So the half-life is actually 5730. So it is years, so that's times 365, the average number of days in a year, times 24, that's the number of hours in a day, and then times 60, that's the number of minutes in an hour, and times 60, that's the number of seconds in a minute. That's my half-life. So we do lambda over that number, log of 2 over that number. That should get us a lambda of about 3.83 10 to the minus 12 per second. And then lambda times n, that gives us an activity of 0.23 decays per second, or becquerels. So this is actually what we have in living organisms. This is the decay rate coming from a person. That's what we mean you are radioactive. In your body, that's made up of mainly of carbon, you have one carbon-14 atom and 8.3 10 to the 11 carbon atoms. So you end up having a decay rate of this much, 0.23 decays per second. That particular value is useful for carbon dating. For example, after we just found that the decay of a living organism is of about 0.23 becquerels or decays per gram. Now, if we find a bone of a nice man that's decaying at a rate of 0.115 becquerels, we can estimate that he died about 6,000 years ago, because this number is just half of that, one half-life away from that. Now, if it is something different than just half of it, we just use the equation. N is equal n0 exponential minus lambda t. We can find the time this way. Now, n0 is going to be our 0.23, and n is whatever the rate is right now.